Okay. Hello, everyone. Welcome. My name is Ganesh Upadhyaya. I'm the session chair for this session. I'm basically an industrial practitioner. I work as a research engineer at Harmony. It's a blockchain startup. I work on Solidity programming language, Ethereum virtual machine, and program analysis and verification of smart contracts. This session is titled Applications, and we have 4 great presentations lined up. A gentle reminder to participants is that please ask your questions in Clouder Slido so that I can go over them after each presentation and give an opportunity for the presenters to answer them. So without further ado, our first presentation is Big Code not equals to big vocabulary, open vocabulary models for source code, to be presented by Raphael from University of Edinburgh. Raphael, you may take over now.
Hi, everyone. My name is Rafael Karambatzis. This is joint work with Hlip Bobby, Roman Ropes, Charles Sutton, and Andrea Yanas. And I'm going to present to you big code is not equal to big vocabulary, open vocabulary models for source code. So our journey starts back in 2012 with the naturalness hypothesis. And that is that software has statistical properties similar to natural language. So inspired by this, several researchers found out that language models were surprisingly effective for source code, and that code properties are stronger inside the project than across projects. So what would a code language model be useful for, though? So there are several applications like autocompletion, improving code readability, program repair, identifying buggy code, API migration, identifier name suggestion, and transfer learning. So what's the motivation behind this work? Basically, we wanted to find the best or a very good way to model software's vocabulary. What's the problem with this? Why is this so hard? Basically, developers are afraid to choose names when they're coding, and they can make arbitrary complex identifiers like the examples you can see on the slides. Furthermore, the out-of-vocabulary rate is basically insanely big. It's huge. For example, even if we use a vocabulary of 11 million in our model, in that case, still 40% of the test set is going to be out of vocabulary. More realistically, you'd use something like, let's say, 75K that's been used in previous work. And in that case, in that scenario, you would end up with 80% being out of vocabulary. Another issue is, what do we do with identifiers? You know, they might still be in the model, but how can you estimate the parameters when you have like only 3-4 instances of those? So even, you know, if you go and say, I'll make a huge token in the LAM, that's going to be impossible to scale beyond a few hundred projects, as it was shown by Hellender and Divampo. Our goal here is to scale the NLM to large corpora, more than tens of thousands of projects instead. So what we did, our first contribution was to study the effect of different vocabulary design choices. So we handled comments, string literals, white space. We also filtered in frequent tokens. We split compound names by underscore or camel case. Then another option is we came up with using BPE to learner segmentation. I'm going to talk a bit more in depth about this later. Basically, what we learned here was that the rest of the choices are not enough to obtain a manageable vocabulary. This is discussed more in depth in the paper, but I don't have time to talk about it now. So what we learned was very useful knowledge for all source code models. Inspired by this, we implemented a BP NLM, and we augmented that with a dynamic adaptation algorithm that adapts the model specifically to your project, and a completion algorithm because the model outputs subtokens, not complete tokens. Finally, we evaluated it on 3 large corpora, more than tens of thousands of projects each, And we also evaluated using bug highlighting, the task of bug highlighting on defects for J. So what is BPE, or byte parent coding? So we start initially with, let's take this example here. We have the tokens protected and private. We start with initial vocabulary of set of characters, and at its iteration, we merge the most frequently occurring sequences of characters together to form a new entry in our vocabulary. And this keeps going on until, let's say, 2,000 or 10,000 iterations. And you can see examples of how code would be split in these two cases. So we end up with a flexible vocabulary. Now we don't have any out of vocabulary words, and we don't have actually frequency issues because we've used the list entropic way to segment. So here's also an beam search algorithm for doing code completion. I'm not going to talk in depth here, but you can, pause it and see it later if you're interested. So the next part is dynamic adaptation. So yes, you might have like a very big model of code, a global model that you can take from like some IDE vendor like Eclipse or Visual Studio or IntelliJ. But then you kind of want to adapt this on your own code, and maybe you don't want to, share your code with them. So to solve this problem, we came up with this dynamic adaptation algorithm that's super fast. An alternative would be, I can train a model on my project, but then that's too small and it's not going to work because you don't have enough data. Retraining the whole thing with, huge corpus is not fast. So the solution was to do this kind of dynamic updates on like small sequences from your project. Then we evaluated using several baselines. So these are like different language models like engrams, nested engrams, CAS engrams from nested CAS engrams from Helena and Ivampo, token neural language model, and a subtoken language model that splits on underscore and camel case. So we use 3 corpora, one on Java, one on C, and one on Python. And we have basically a large train set, a smaller train set, a very small set where we learn the encoding, a validation, and a test set. And you can see statistics later by pausing on rewriting. So the evaluation is happen on 2 tasks. One is code completion, and there we measure cross entropy, which basically measures the degree of prediction of certainty, and then mean reciprocal rank, which is the average of the inverse of the rank of the correct answer. Then the other task is bug detection, where we measure the entropy drop on bug fixes. So here are some results. I'm not going to talk about them. You can look at them so we did very detailed evaluation, which you can find in the paper. Basically, in this extensive evaluation, our model reigns supreme in most or almost all cases, actually. So to finish, everything is available. The model, the code, all the corpora we used. We have basically this very, very tiny BP neural language model that's dwarf compared to huge models in the past. Thank you.
Okay. Thanks for your talk. It's a wonderful presentation. I don't see any questions in the Clouder, but I have a question. Maybe people will ask more questions later on. So please feel free to hang around in the Slack and places to answer the question. So my question is, can you explain some of the real world use cases of your work?
Sure. The simplest case would be, while you're writing code, you can do very effective code completion. That's one thing. Another thing is, though, you can use this thing in, for example, to highlight bugs, as we saw in the papers. The thing is, by finding certain, let's say, statements that the model thinks that are very unreasonable, these are very good candidates for, to augment like a static analyzer or any other program repair system. Apart from that, though, another thing is that our model learns actually representations for the code. and you can do transfer learning and take these representations and use them basically in any sort of task, like any sort of classification for code. This is something that happens very commonly actually in NLP at the moment, and it's a very hot thing to do this sort of transfer learning with language models.
Yeah, thank you. I see some more questions here. So Shivali asks, how do you think this will impact topic modeling task?
It's a good question. So I'm not sure what the answer would be in the case of topic modeling, but I think you could basically use this in some sort of clustering actually of code, maybe finding, similar code instances based on the model. Maybe a thing you could do is by adopting like the model on, specific projects, you can see how close they are and how much the model changed, for example. That would be like something that came, quickly in my mind.
Yeah. There's one more question. What do you do with the non-dictionary terms?
So this is why we call this open vocabulary model. You shouldn't find basically anything that's out of vocabulary except if it's like some very strange, Unicode character. Because in that case, the model is what it's going to do. Worst case is it's going to segment everything into characters. But that's going to happen like super rarely. And, even when it splits into characters or very small character sequences, those are going to be in the model and are going to be frequent as well. So that's the trick there.
Yeah. Thanks again. There were a few more questions, so feel free to go to the Clouder and try to answer them.
Sure.
We are almost out of time. You can unshare now. Thanks again for a wonderful presentation.
Thank you very much.
Yeah. Moving on to our second presentation. It's titled Engineering for a Science-Centric Experimentation Platform, to be presented by Jeffrey from Netflix. So Jeffrey, you can take over and share your screen now.
Thank you so much for hosting me. I'm going to start my screen share right now. And for today's topic, I'm going to be talking about a talk that I want to call Engineering for a Science-Centric Experimentation Platform. And I'd like to walk you all through a pretty transformative journey that made the Netflix experimentation platform science-centric. And this is going to be a journey that led our engineering teams to develop experimentation frameworks, grammars, and programmatic interfaces that leveraged and were inclusive to data scientists and their domain expertise, which was critical for us to deliver a top-tier platform for online experimentation. So at Netflix, we use experimentation in multiple parts of the business, including product, operations, growth, and even artwork. Imagine you open up your TV. How should Netflix use visualizations to showcase all of its content? When it comes to Stranger Things, do we use artwork to highlight the kids in the show, or the fact that it's a thriller? Or perhaps maybe we should use different artwork that will attract different types of users, like maybe this throwback feeling to people that grew up in the US in the 1980s when Ghostbusters came out. And we optimize the artwork through data and experimentation, and we also relay that information to our partners creating the images. Now, in order to support hundreds of other experiments that are happening at Netflix, we need a powerful experimentation platform. And the typical architecture for such a system starts with data logging. Who is in the experiment? What are the KPIs? And what are the other important dimensions? For example, how long has a customer been a subscriber with Netflix? And after the data logging, there's a series of Spark jobs that joins together several tables and calculates statistics for users, like the total number of hours streamed or the total number of retained users. And these statistics are then loaded into Elasticsearch or Druid for fast indexing and querying. which ultimately serves the platform's interactive dashboard. The trouble with this architecture, though, is that there is an explosion of technologies that are difficult to manage. And furthermore, it's difficult for data scientists to contribute. As software engineers, it's kind of our responsibility to keep up with cutting edge software, but it's not really a scientist's responsibility. And so Netflix was not fully leveraging its top data scientists. So to change that, we recognized that the design patterns for the experimentation platform needed to be science-centric. And in order to do this, the platform needed to be designed with 3 key tenets: trustworthiness, scalability, and inclusivity. And we want to be inclusive to that group of data scientists. The first 2 tenets you all know, but to accomplish this while being inclusive is hard. But being inclusive is also necessary in order to let scientists from diverse backgrounds contribute their unique domain knowledge to the platform. And being inclusive meant we needed to be open to languages like Python and R, and be ready to absorb packages like pandas, stats models, and dplyr. So moving towards a science-centric experimentation platform, we engineered a few narrowly scoped libraries that allowed data scientists to contribute to data, modeling, and visualization, while still preserving key engineering principles like trustworthiness and scalability. The 2 libraries I'm going to talk about in detail are Metrics Repo and Causal Models. Metrics Repo is our Python framework for orchestrating data, analysis, and rendering of reports. It allows data scientists to make targeted contributions for the platform while preserving its trustworthiness and scalability. Metrics Repo enables a pattern for data that allows users to compose and contribute programmatically generated SQL that runs on Spark. And this programmatic nature supports Metrics Repo's open and inclusive policy for contributing data sources. In this example, a user is building a query class that interfaces with tables in order to auto-generate SQL, removing hard coding and allowing safe inheritance. And Metrics Repo also ships a powerful testing framework that includes unit tests and integration tests, analyzing data end-to-end, guaranteeing consistency in data sources and metrics. And this framework creates an attractive environment to centralize data and metric definitions in a standard way, supporting the scalability of the data store. After configuring the data, users can also configure the analysis options for their metrics. For example, they can specify that their metrics are proportion metrics or rare event metrics, which subsequently configures the analysis appropriately. And they can also configure the visualization for their metrics. The metrics repo takes care of an enormous amount of surrounding engineering infrastructure in order to support data science contributions. For scalability, it parallelizes computation and spins up extra machines to handle load. It also lets data scientists make simple code merges that auto-trigger deployments of new data, new metrics, and new metric configurations, which automatically render in our dashboards. The second library I'll talk about is Causal Models, which is our Python library for statistical models that analyze causal effects. In this example, we are utilizing different models in order to produce a rich analysis of causal effects, ranging from the average effect in an experiment to the average effect for a segment of users to the average effect in trends in the effect for a segment of users. And like Metrics Repo, it centralizes and standardizes implementations for models that are relevant for the experimentation platform. The library continues this theme of having an open contribution policy and has seamless integration with Metrics Repo so that all statistical models are automatically included in experimentation platform's deployment process. And after contributing a model, a user can use Metrics Repo to configure their metrics to be analyzed with this new model. Causal Models is a highly optimized library in order to give data scientists a library that computes causal effects efficiently. And we are able to compute hundreds of causal effects on large data sets in seconds. In order to achieve that, first, all of our numerical computing happens in C++, where we can control memory efficiently. And second, we utilize a data compression strategy for conditionally sufficient statistics that shrinks data volume to the point where it can fit on one machine. And finally, the library is optimized for sparse linear algebra. And all of this are software improvements to help data scientists scale their code. The library is so efficient that they can run analysis on just their MacBook. And the fact that the same analytical production tools can run on their machine changes the culture and empowers them to make direct contributions within the XP's open policy. The separation of the libraries allows easy contribution, but the libraries also retain strong interfaces to bridge them. Users of the experimentation platform can toggle the way they analyze an experiment to suit their data and their assumptions. And they can pick any combination of metrics, models, and viz, which create a very attractive environment for anyone to explore and to learn. And to conclude, I want to share the impact of this shift into being more science-centric. The integration of libraries and tools that data scientists use has increased the learnings our platform can offer. And the platform is able to better leverage models for analysis. And those new models improve sensitivity in our metrics, sometimes by 60%, and show deep insights into the dynamics of segments of users and trends. At the same time, the integration has improved our human efficiency. Team leaders can rely on the fact that the platform can be developed by both software engineers and data scientists. And we currently have 80 contributors to this framework, amplifying learnings and collaboration. There is a larger interdisciplinary focus going across both communities, and it has created a technical symbiosis where data scientists are gaining skills and spending less time productionizing their work, and in turn distributing their domain expertise to improve the company. Thank you all for having me, and please reach out if you'd like to discuss more.
Okay, thanks Jeffrey for your wonderful presentation. Yeah, there is a question here. Is any of your models and libraries open source?
Currently not at this time.
Okay. Yeah, I have one question. How long the typical experimentation at Netflix take, and what is the cycle looks like in terms of adopting the findings of the real, experiments?
The experimentation life cycle spans a couple of weeks, and that includes a lot of human components, from forming a hypothesis for business strategy or for business operations. And then from there, we work on the engineering to be able to test out the hypotheses. And then we conduct an experiment, for example, in streaming operations or content delivery, to be able to figure out if the new hypothesis can be confirmed or not. And we'll monitor our KPIs for a couple of weeks in order to be able to make that conclusion.
Okay, thanks again for your presentation. You may unshare your screen now. A general note to the viewers is that you don't have to wait until the end of the presentation to ask your question in the Clouder. You may ask right away so that I can start collecting them and ask the presenter. Okay, moving on to our third presentation titled Managing Data Constraints in Database-Backed Web Applications. And our presenter is Junwen from University of Chicago. Junwen?
Hi, everyone. I'm Junwen. Can you see my slides and hear me?
Yes.
Okay, cool. I'm from University of Chicago, and thanks for Ganesha's introduction. And I will be on the job market, so hire me and feel free to reach out to me And this is a joint work with University of Chicago, University of Washington, and UC Berkeley. So we're working on managing the data constraints. First of all, data constraints are associated with data to describe their properties. In this given web page, you can see that there might be a lot of constraints associated with the title box, such as the presence, a length, uniqueness, or format. And also in web applications, there are a lot of data to process with many constraints. And our study has shown that 77% of the fields are associated with constraints, and on average, 1.4 constraints are associated with one field. Also, the constraints can be specified in multiple layers. For example, in the Reels application, the front page can specify the length requirement using HTML input tag, and also the application can specify the same constraint using the Rails validation function. At the same time, in the backend database server, you can use SQL queries to specify the constraints. These applications often face very frequent upgrades and migrations. For example, their data schema might change from one version to another, which also happens to their front end and application code. So people may have troubles to manage their data constraints given this altogether. So in our previous wiki page, when I tried to create a title which has more than 51 characters, and then I click the next button, it works well, and I've been guided to the page which allows me to type the body. So I did some typing here, and then I do the save button. What happens here, it gives me a red page full of errors, which makes me annoying. So I go back to the page. I'm thinking that my content might have something wrong. So I try to re-edit it, and then I try to save it again. However, I still got this red error page, which is super annoying because I have lost my contents that I have added for a long time. What happens here? The constraint inconsistency happens. Since the application and the front end has specified the maximum length of my title to be 60, but the database here uses a variable char to specify the maximum length of my title to be 30. So the title with 51 characters, which pass the check of the front end and pass the check of the Rails application. However, it will fail the check of the database. So as the result, in our work, we try to understand the real-world data constraint problems, and we try to tackle them. To achieve this, we have conducted an open source study on 12 open source Rails applications from 6 popular categories. And then we randomly sampled 114 issue reports from their issue tracking systems. We also automatically extracted 7,000 constraints from their latest versions. By manually studying these 114 issue reports, we have categorized 4 anti-patterns, which are inconsistency of where the constraints are specified, inconsistency of when the constraints are specified, and inconsistency of how the checking results are delivered, and inconsistency of what the constraints are about. We will introduce them one by one. The where issues happen when constraints under different layers conflict with each other. It could be the constraints in the applications is weaker than those in database. In our previous example, the application has 60 as the maximum length, and the database has 30. The title of 30 to 60 of characters will cause the page crash with unhandled database error. On the other hand, when database has weaker constraints than application, for example, in Spree, which is an online shopping application, the product is specified in the application to must have one price. However, these constraints are not specified in database, which allows the admin user issues SQL queries to delete certain price of corresponding product. As a result, the page which displays the price and its related stuff will crash with application error. This type of anti-patterns cover 24 issues. And the inconsistency of when issues happen when upgrading an application. The newly added or changed constraints are incompatible with the old data. For example, in GitLab, which is similar to GitHub, its version 4 have added a new field named HTML, and it allows it to be null. However, in version 5, they have changed the requirement to does not allow the null value. As a result, during the upgrade, the migration will fail since the null value records created between version 4 and version 5 will fail the not none constraint. And for inconsistency of what issues happens when the constraint conflict with either the user or the application needs. For example, still in GitLab, when you try to create a user named Bob, which is lowercase, you will be told that the user already exists. Try other names, since the newly created usernames are case insensitive, and they already have someone called uppercase Bob. But when you try to send a message to Bob, you type the lowercase Bob in the to box and click the save button. The application currently will tell you that the user does not exist, since they retrieve the username in a case-sensitive way. The conflicting behavior affects the user experience and is subtle to detect. After understanding these constraint problems, we tried our best to tackle them based on these anti-patterns. For where issues, we have automatically extracted 7,000 constraints in the latest version and break down them according to where they are specified. And we compare them across layers. We found that 400 of them, which are specified in the application, are actually not specified in the database. And vice versa, there are more than 1,000 string length constraints that's specified in the database, which are not specified in the application. And not to mention, there are also more than 100 cases that they conflicting in the detailed requirements. All this might cause the page crash with unhandled database or application error, as we have mentioned before. And to tackle with how issues, we have developed a new gem for better error messages, and which is also open sourced. And to tackle the what issues, we have automatically detected 19 case sensitivity conflicts in their latest version. And we reported to the developers, and they confirmed that some of the code are already merged into their code base. And also to tackle the when issues, we have built a tool to automatically detect when conflict. So in conclusions, we conducted the first in-depth study of data constraints in database-backed web applications, and we categorized 4 anti-patterns for data constraint issues. And we also developed a checker to detect the data constraint issues. That's my talk. Thank you. I'm on the job market.
Okay, thank you very much. That's a wonderful presentation. I have a question. Maybe I missed. What are the databases did your experiments covered, and were there any differences in terms of impact across databases?
Oh, you mean the type of database we're doing experiment?
Yes.
Actually, for all the applications, there are 2 types of database, just pSQL and MySQL. They're most popular 2 databases used in the real applications, and that's what we are studying. But actually, for the constraints that we extracted from the applications, they're specified by the queries, which are not, which will not be affected by the type of database.
I see. And follow-up question, did you try to approach and apply your technique to any industry product?
So actually, we try to expand our scope from not only web applications, but distributed systems. That's our future plan. But yeah, I think we can try find some industry applications too.
I see. It's very, very interesting. Thanks again for your presentation. Feel free to hang around in the Clouder to answer any further questions. Thank you. Moving on to our final presentation, titled Improving Data Scientist Efficiency with Provenance, to be presented by Jingmei from Harvard University. Jingmei, you may take over now.
Is my screen shared?
Yes.
Okay. So, hi, I'm Jingmei Hu from Harvard. Today, I'm going to talk about a novel way to improve data scientist efficiency with provenance. This is a joint work with Jiwon Zhang, Maya Jacobs, Shishto Styles, and Marco Seltzer. So everyone knows data science is important. Data scientists frequently analyze data by writing scripts. They typically arrange their script into a iterative procedure which consists of editing the script, executing those scripts, inspecting the results, exploring parameter alternatives, or debugging, and then editing the script again. Meantime, parameter tuning accounts for the majority of development time, and debugging is both time-consuming and cognitive load demanding. So how can we make this script development and debugging procedure more efficient? So we make a hypothesis that isolating and streamlining the piece of code that the user are working on can expedite the data analysis process. So our work is we develop ProfView, a tool that uses change impact analysis to improve script-based workflow pipeline. In particular, we use language-level provenance, which records information about every lines of code executed by a script. It identifies the dependency and we will identify the dependency between all data objects. In order to help reduce programmers' cognitive load during debugging and decrease the subsequent execution time, ProfView pinpoint which part of program and statement must be re-executed to produce a new result, and generate a shortened script called ProfScript that contains only the section relevant and affected by the modification. The purpose of generating this small script is to make it easier for the user to reason about their code. We evaluate our work with 3 studies: a control lab user study, a performance benchmark, and a real-world deployment. So first, I will show a toy example. This toy example shows how ProfView works. The left script shows the original script that we are trying to debug. Assume that the debugging target is function bad in line 5 and 6. ProfView utilize no workflow to collect Python provenance and analyze dependencies relevant to this target bad. Then ProfView will generate a shortened ProfScript on the right, which contains the definition of bad and the subsequent assignments relevant to bad, which is lines 9 and 14 on the original code. Other irrelevant variables are treated as constants, which is line 1 to 4 in the ProfScript. As we mentioned before, ProfView use no workflow to collect language-level provenance for Python scripts. And with the generated provenance information, ProfView constructs a provenance graph for the debugging target. Given the target, we divided the execution provenance into upstream provenance, which is everything on which the target depends on, and the downstream provenance, which is everything that depends on this target. ProfView iteratively collect those dependencies and include them in the ProfScript. Meanwhile, provenance is execution trace information. There are some aspects of the script that ProfScript needed, but is not recorded in the provenance, such as control flows, including every possible function related to overly complicated ProfScript. So ProfView develop a iterative exception handling method, which ensures that we are not missing anything and we don't include unnecessary parts. ProfView also automatically integrate changes into the original script. So here we show a simplified ProfView interface, which contains the major functionality for ProfView. Search is for specifying the debugging target, and ProfView will generate a ProfScript on the backend for the user. Execute is to execute the modified ProfScript, and merge is to integrate the changes. We use this interface for our user studies. So our first evaluation is a control lab user study. We use multi-hypothesis p-value testing to evaluate 3 hypotheses. Prof-use will decrease task completion time, user cognitive load, and users are subjectively preferred to use prof-use. We conduct this study with 21 participants and 4 debugging tasks. For more user studies, please refer to our paper. The p-value result shows that there is a significant difference between debug with or without prof-use, and the results support all the hypotheses. This study quantified prof-use ability to reduce cognitive load and execution time for debugging. Our second study is a performance benchmark. This study answers 2 research questions. How much overhead no workflow will introduce, and how much speed up prof-use can produce? The results show that prof-use takes a while to start up, or say initialization, but then the debugging and editing cycle are shorter. The major of this initialization overhead is due to no workflow dynamic performance prevalence tracking. We treat it as a limitation and future work for prof-use. In the next user study, users did voice some concerns over this initial runtime, but not enough to prevent them from using prof-use. As for speed up, we categorize 3 kinds of changes and compare lines of code and re-execution time between the original code and the code that prof-use generated. Even in the worst cases, there's class C, which is change some input variables. Prof-use can still get some speed up. Our last evaluation is a real-world deployment. We gave user access to prof-use for a week and obtained their feedback after they use it. It shows that participants express a preference for using prof-use and do not report any significant barrier for individual usage. They also address several issues, and please refer to our paper. This evaluation shows the usefulness and efficacy for prof-use. So to conclude, prof-use is a novel use of language level provenance. It helps users focusing on the debugging code and avoid unnecessary changes. It makes it easier to reason about code and reduce the cognitive load for debugging, and prof-use also reduces subsequent execution time. So prof-use is easy, effective, and efficient tool for the user. And prof-use is available online now. Thank you.
All right. Great work. Thank you, Jingmei, for presenting. I see a question. Can ProBuild handle changes in data and code, or only one?
Sorry?
Can your tool handle changes in both data and code, or either of them?
Yeah, we can only handle the changes in the code, not the data. If it changes the data, we treat it as an input variable changes. So that's categorized as like some input changes.
I see. So I have a question. What are some of the future directions of this work?
So as I mentioned during the talk, we noticed a really relatively large initialization slowdown, which is due to no workflows prevalence collection. So for that part, we consider as a future work for prof-use, which is like prof-use only needs subset of the real prevalence information, and perhaps we could improve some kind of initialization for prof-use.
Okay. Again, thank you for presenting. Okay, that marks the end of this session. First, I would like to thank our Zoom host and producers. And also let's thank our 4 wonderful presenters, Raphael, Jeffrey, Junwen, and Jingmei. And finally, all the participants for attending this session and asking questions. Thank you. Next session will start in a few minutes. Stay tuned. Bye-bye.
Hello, everyone. Welcome to EC 2020. This is the session P30, Ecosystems Number 2. I'm Chang Xu from Nanjing University in China. I'm mainly working on engineering for intelligent software and testing for adaptive systems. I'm chairing this session. Okay. In this session, we have 4 presentations. One is journal first paper presentation, and the other 3 are technical check paper presentations. Audience, please raise your questions in Slido at our cloud webpage. And you can also vote your favorite questions there. Okay, so our first presenter is Tao-Hai Gallagher. He is the final year PhD candidate from Queen's University in Canada. His paper title is Studying the Impact of Noises in Build Breakage Data. Tao-Hai, are you ready?
I am ready.
Okay, please go ahead.
Hi, everyone. I am Tahir Galip. In this talk, I'll be presenting our work in collaboration with Daniel Da Costa and my PhD supervisor, Jenny Zhu, and Ahmed Hassan. So our study is about the impact of noises in build breakage data, in particular, continuous integration data. So first, continuous integration is a software practice that allows developers to automate their builds so that they can identify bugs at early stages. And it allows developers to run their builds under multiple environments. CI builds are not always successful. They might break due to errors happens in the installation phase, like installing dependencies, or failures in the compilation or testing. However, build breakages are not always related to developers' code changes. They could be incidental, which might gives an overhead to developers, because sometimes developers, they keep waiting for the person who broke the build to fix it, but he's not actually the one who broke it. And sometimes they have to do some unnecessary changes to fix the breakage without being able to fix it. Let's take the following example. We can see a bunch of build breakages or errors, and it can tell us that when the first build got broken, the developers tried to fix it until they got it right. But looking deeply to these builds, we can see that some of them are actually environmental. They got broken due to the environment, not the code changes. And we can see here that those breakages are just cascading the very first breakage that wasn't fixed by developers. So these breakages are introducing noise to build breakage data. Here's another example where certain jobs cause the build breakage. But we can see here that developers at later stages, they exclude these jobs by removing them or allow them to fail without failing the builds. That means that if these jobs were excluded earlier, the previous builds could have passed. So these kind of build breakages also introduce noise to build breakage analyses. Therefore, in our study, we studied the 3 types of noisy build breakages: the environmental, cascading, and allowed breakages. And also we studied the impact of such noise on prior findings of research findings. So we took a Travis Turin dataset, and then we took the projects that have enough builds for our analyses. So we got 152 projects. We also took a dataset from a previous study on build breakages. So we took these datasets, we downloaded the build logs, we analyzed them, and then we excluded the noisy build breakages from the dataset using the 3 criteria, the 3 types of build breakages. And then we reported the proportion and types of noise in build breakage data. Then we cleaned the dataset from these noisy build breakages, and we built regression models on the cleaned and noisy datasets to study the impact of such noise on prior findings. So we identified 55% of build breakages in our data set. They are unlikely to be related to developers' changes. They are noisy. They are either environmental or cascading or allowed. And we could identify 60 types of environmental build breakages, with the majority of them caused by internal CI errors, external connection errors, or timeouts. With 2/3 of them are exclusively environmental. That means like developers cannot fix them. Only 15 subcategories of these, developers could find workarounds to fix them or avoid them. So when we model the build breakages using a clean data set, we find an improvement to the modeling performance by 6% AUC. And also we found that the noise might make a regression model sensitive to language, project, and build ages. So we also found that the noise in build breakage data may lead to misleading conclusions. For example, the time of day in the clean data is not associated with build breakage, but the noisy data is associated, but in the noise is not. Same thing for developers. They are not associated after cleaning the noise. And also team size, they are not actually associated with the build breakages as the noisy data says. We also studied, as I said before, a data set from a previous study. And we found that findings of prior research on build breakages may not hold. For example, in the prior study, they found no significant influence of the day of week and time of day on build breakages. However, after cleaning the data, we found that there is a significant influence of these variables. The previous study found that pull requests cause more build breakages, but after cleaning the data, we found that integration and merge commits cause more than that. Also, the prior study found no evidence that certain file types cause more breakages, but cleaning the data shows that system files actually cause more breakages. And finally, the prior study found like less frequently developers, they cause fewer breakages. And after cleaning the data, we found that in addition to that, also daily committers can cause fewer breakages. So let's take these home, take-home messages. Developers need to restart broken builds if they feel like the results or the status is unexpected. Researchers should carefully clean their data set when performing analysis on build breakage data. And finally, the CI services should give more details about the status of builds, about the breakage itself, more details about that. So these are the key points of my presentation. And if you are interested in more details, you can access our paper published in TSE. Thank you.
Thank you, Dao Hai. Since we don't have questions from audience right now, let me ask the first question.
Sure.
In my opinion, you try to separate the environmental factors from basic normal development activities. But still, I think such environmental factors like timeouts, connection resets, and memory allocation errors can still cause configuration errors or installation errors. So why still consider them as noises?
Right, because like in the prior studies, they try to model build breakages. They try to predict whether these commits or these coded changes will cause the breakage. And they consider these builds as they were broken by those commits, but they are not caused by those commits. So how shall we use these commits as predictors for the breakage while they are not actually related to the breakage? So they introduce noise to the regression models.
Okay, thank you. Okay, we have one question from audience.
Sure.
How many CI systems, continuous integration systems, did you consider in your study? And how reliable?
Only one. Yeah, only one, Travis CI. Yeah, Travis CI. We took 152 projects, GitHub projects that are linked with Travis CI.
Okay, so time's up. Thank you for your answering. Thank you for your talk. Okay.
Thank you so much.
Okay, the second presenter is Lin Chao Chen. He's from UC Dallas. He is a senior PhD student majored in computer science. His research mainly includes regression testing, mutation testing, and machine learning-oriented software engineering. So, Lin Cao, you are presenting taming behavioral backward incompatibilities via cross-project testing and analysis. Are you ready?
Yeah, I'm ready.
Yeah, please
Hi,
go
everyone.
ahead.
Yeah, hi everyone. This is Lin Chao from UT Dallas, and my advisor is Lin Min. Also, I'm Xiaoying from UT San Antonio. Today, I'm going to present my XC paper, Timing Behavior Backward Incompatibility with Cross-Project Testing and Analysis. First, let me introduce what's a backward incompatibility. It widespread in both commercial and open source libraries. Where library get upgraded, some changes can break the existing functionality. For example, we have our old version and include some old APIs. When it upgrades to the new version, some API change, some API not. For MR, M2 here changes, and the bug due to this change, we call it the backwards compatibility bug. For this problem, it's very hard to detect and have serious impact. Recently, there is a news named another one-line NPM package broke the JS ecosystem. According to the GitHub, there are more than 3.4 million projects and 766 other JavaScript libraries get involved. Facebook, Google Maps, Firebase, Amazon, all these companies get involved in this issue. And usually developers use regression testing. They run all the tests after upgrading to check if the changes break the existing functionality or not. For example, the Commons VFS upgrades from the 2.2 to the 2.6, and here are the test suite and the API they cover. From our experiment, we found the URL file name parser have a bug, but only run those tests cannot detect it. And here is a repository growth graph for the Maven repository and GitHub repository. Until now, there are tens of millions open source projects we can use. So we proposed our technique named DEBBI. We use cross-project testing and analysis, which means we use large number high-quality client project test suites from different client projects. However, it involves a huge testing effort. So we try to further transform the backwards incompatibility detection problem into a traditional IR problem. For example, here is Commons VFS, the same example, and here are a bunch of client projects and the test suite in this project, and the library they covered. And when it upgrades to the 2.6, still the same APIs, URL file name parser changes, and there is a bug. And we run all the client projects, all the tests which touched this change. And here is the overview of our technique. Totally, there are 3 parts. We generate the index from the source code as a document. Meanwhile, we generate diff change as query, and we retrieve which project could be the most relevant one, may have the BBI bug, and get the list of those ranked projects. And for the first part, we extract the class and file changes between old version and new version as query. Here, still the 2 versions of Commons VFS, we get the diff information, and we get the class changes, and we build our query. And for the second part, we use static analysis to extract the library usage of each project as a document. We get a bunch of source code files from the client project, and we analyze them and get the library usage and conduct them into the index of document. And for the retrieval, we use the traditional information retrieval to prioritize the client projects. We have our diff, which include 2 changed API, and there are 3 projects. We can see the P2 is more relevant to this diff. So after the retrieval, the execution number would be the P2, P3, and P1. And for our first optimization is we use the information retrieval with MMR to increase the diversity. So MMR is an algorithm which can solve the diversity issue to improve the IR performance. And here we have a diff which includes 4 changed API. And P1 and P2, they share the same API. And if we just use the traditional IR, they should have the highest rank because they are more relevant to this diff. However, because they share the same API use, then the bug behind them might be the same. So after IR with MMR, our execution order would be the P1, P3, and P2. Then we can early detect the different type of BBI bug. And second optimization is we use the regression test selection. We use static analysis to get the dependency of each test, and we only executed affected tests to further speed up our detection. Here we have 3 projects and their tests and change the API to cover. And through the RTS, we only run the P2, the T2 in P2 and T1 in P3, and now the test covered touch the affected API. So now the test executed in P1. And for our experiment, we have 2 sets experiments. One is for the widely used JDK. The other is for the third parties. And for the JDK part, we use nearly 3,000 open source projects. And for the third party, we use 100 library and around 40,000 open source GitHub projects. And for the evaluation metrics, we have 3 metrics: first, average, and last. The metrics reports the performance, the time taken, the number of projects executed, the number of tests executed to identify the first, each, and last BBI bug. And here is the improvement for our JDK test execution time. From the graph, there are 4 techniques: the random, LDA, LDMMR, LDMMR, RTS. The random is our benchmark, and the cluster here means we target on each different type of BBI bug. And through the graph, we can see LDA and MMR, RTS achieve a huge improvement. And here is our result of detected bugs for the third-party libraries. We report 97 bugs to the developer of those libraries, and 54 confirmed as known bugs, 19 confirmed as unknown bugs. And here is the overview of our detected unknown bugs. The column project name, the start in the GitHub, the client project number, and reversions we use in our experiment, and the unknown bug number. And here is the first example from the third core. So the method contains only keys, cannot handle the case when it was involved on our map with the key type is passed, and you confirm as a previous unknown bug. And so first we build the map and the key set is passed. And when we invoke this method, the test failed. And for the second example is from Commons VFS. The method pass UI will fail to pass the UI when the first 2 parameters are both none and the UI includes a substring like this. So we still build a string like this and put the first 2 parameters as none, and then call this method pass the UI, and this test failed. And here is the third example from the JSoup. The developer forget to deal with the situation when the end of the string in method select is a space. So we still try to build our string and end with our space and try to call this method select. The test also failed. And all those test cases are from real-world projects, which are hard to generate by the automatic generation tool. And here is a conclusion from our paper. We leverage cross-project testing and analysis to detect BBI. And we transform the BBI detection problem into a traditional IR problem. And we further optimize using the diversity of different projects and cross-project RTS to further speed up detection. And we discovered 97 bugs for the real-world libraries and 19 are previous unknown bugs. And that's all my talk. Thank you. And any questions or comments?
Thank you, Ling Chao. Still, I'm asked the first question.
Yeah.
It seems that the work focuses more on the efficiency of the testing. So how about its effectiveness? For example, can you talk more about the detected false positives and negatives? Is that okay? Because I think it may contain more potential impacts to users.
Yes, actually, there are more detail about the false positive discussion in our paper. Like if the audience are interested, they can go to our paper to read them. And I can also talk about something more about them now. Like there definitely are some false positive in our the experiments. Like for example, there are some bugs are not caused by some API change. They are made because we are based on the Maven project. So some are caused by the POM file or something else. Yeah, they do have some false positive, and we have discussion in our paper.
Thank you. There's one question from the audience. What's the proportion of cross-project bugs with respect to local project bugs? Cross-project bugs versus local project bugs. I guess he wants to know which is more and why. Some observations.
Yes, actually, we detected bugs which is between like the two versions, where there is an old version and there is a new version, and we detected those frequent changes between this old version to this new version, which means those bugs are conduct from this new version because they upgraded. The developer didn't realize they changed something and caused those bugs.
Okay, thank you. Time's up. Thank you for your talk. So next, our presenter is Ying Wang. She is an associate professor with the Northeastern University in China. His talk's title is Watchman, Monitoring Dependency Conflicts for Python Library Ecosystem. So Ying Wang, are you ready? I guess you need to switch the, yeah, perfect now. Please go ahead.
Thanks for Chang's introduction. Hello, everyone. I'm Wang Ying from Northeastern University and also a member of Causal Research Group. Today, I would like to present our paper entitled Watchman Monitoring Dependency Conflicts for Python Library Ecosystem. Python projects are commonly shared as third-party libraries in a server-side central repository, PyPy, and reused by many other projects. By May 2020, the PyPy ecosystem has indexed over 1.8 million Python libraries. This is a common development scenario of Python projects. Most of dependencies are stored in the PyPy ecosystem. The build process and dependency management are automatically implemented by combining a server-side central repository and client-side library installer pip. To be more specific, the local environment should pre-install the Python toolchains or may locally pre-install some libraries if needed. In a project's configuration script, developers should specify all the required third-party libraries with a corresponding compatible version constraint. With the aid of such configurations and the library installer pip, all the specified direct and transitive dependencies can be automatically downloaded and installed. The installed library version is the latest version satisfying the version constraint. As we can see, in a Python project, there are two types of dependencies. That is the local and the remote dependencies. The version constraint mechanism enables automatic self-evolution of the remote dependencies. In addition, for Python projects, all its direct and transitive dependencies are called its upstream projects, and the projects depending on it are called its downstream projects. So that among the complex dependency relationships in the PyPy ecosystem, such automatic building comes with the risk of potential dependency conflict issues. In the Python world, if the same library with different version constraints are introduced in projects, then according to pip's installation rule, only the first found library can be installed. Pip adopts breadth-first traversal strategy to install the libraries. So if the installed version of a library violates its other version constraint on the same dependency tree of a project, then a build error will happen. However, the real-world bugs are far more complicated in the open source community. Taking the issue reports in project channels as an example, channels version 2.1.7 directly depends on two libraries, sgrave and Daphne. Before April 9, 2019, there are no dependency conflicts. However, with the evolution of the libraries, Daphne released a newer version 2.3.0, which can be installed in the project's channels. So here comes the question. The newer version of Daphne introduced a library sgrave again with a conflicting version constraint, causing a build error in the project's channels. To address this issue, channels developers revised the version constraint of the library sgrave in a fixed version, but the story is not over. After April 14th, the fixed version of channels also affected downstream project's channels readies, causing another dependency conflict issue. In fact, This real DC issue is only a tip of the iceberg in the Python community. Developers' complaints about dependency conflicts can be seen everywhere in the open source community. Because lack of a global view of the version constraint among large number of Python projects, developers complained that some library version constraint only can specifically work in their own project or only can work on their own machine, but causing more conflict issues in many other projects. From the comments, we can observe these two obvious challenges. The version of a library installed for a Python project can evolve over time. When a library updates its version constraint on its depending libraries, its upstream projects could be affected. What's more, the state-of-the-art tools like Vue or Poetry and so on only can show which libraries have been installed, rather than the full dependency graphs. So the developers are looking for effective tools techniques that can help them generate full dependency graphs for their Python projects when diagnosing the dependency conflicts. As such, there exists a third challenge. It is difficult to obtain a full dependency graph with version constraint for the projects on PyPy. To address these three challenges and help developers combat these issues, in our work, we first conducted an empirical study to understand the characteristics of these issues. The distilled common patterns enables automatic diagnosis. We also investigated how developers fix their dependency conflicts in their Python projects and summarize the common fixing strategies. Furthermore, we propose a technique, Watchman. It can perform holistic analysis from the perspective of the entire Python ecosystem to continuously monitor and detect dependency conflicts caused by the daily library updates. Finally, we evaluated our approach based on collection of open source projects. By analyzing our collected issue reports, we divided these issues into two patterns, according to whether the issues caused by remote dependency updates or affected by the local environment. For each issue pattern, they can be further categorized based on where the dependency conflicts come from. That is, the conflict between direct and transitive dependencies and the conflict between transitive dependencies. Based on our empirical findings, we propose a technique Watchman. It first constructed a metadata repository for all the libraries hosted on PyPy to enable the analysis of the interference between the version constraint across downstream and upstream projects. Then, by continuously monitoring the library release information on PyPy, it synchronously updates the metadata repository to precisely model the dependency relationships. For the captured library updates, Watchman identifies all the potentially affected downstream projects based on the PIP's installation rules. Finally, it performs automatic DC issue diagnosis. To summarize, the main features of a Watchman include performing holistic analysis for the entire PyPy ecosystem, simulating the process of installing dependencies, submitting the issue reports and PRs automatically, and providing self-diagnosis service. To evaluate the effectiveness of our Watchman, we play back the evolution history of all the libraries on PyPy in the past 5 years and use the resolving rate and lasting time as a metrics. For the predicted issues, we also checked whether they had turned into the real ones. Our obtained satisfactory results strongly demonstrate that Watchman can precisely detect and predict these issues. We also deployed Watchman to monitor the PyPy libraries and evaluate its usefulness based on developers' feedback. In total, Watchman detected and predicted 279 real DC issues during the following 2 periods and achieved high confirmation and fixing rates. All the daily library updates information on PyPy captured by Watchman and our detected real DC issues are released on our website. Besides, we also obtained several positive feedbacks from developers. For example, they saw that using a bot like Watchman to inform the potential dependency conflict issues on GitHub is the best solution for Python projects. And such a mechanism of maintaining the rationality of dependency constraint among the projects on PyPy is much needed. Recently, we also promoted our Watchman in the open source community by communicating with developers. For research purposes, we recorded how visitors interact with Watchman website from December 2019 to January 2020. Altogether, Watchman has generated diagnosis issue reports for 2,590 Python projects. Level statistics demonstrate that the real-world developers show their great interest in our proposed technique, and we also warmly welcome more researchers and Python developers to try out and test our tool, Watchman. That's all for my presentation. Thank you very much for your attention. Any questions?
Thank you, Yingwang. Okay, we have a question from the audience. How does your result in this paper help developers?
Okay, I think the results means our empirical findings. Our empirical findings summarize some characteristics of the dependency conflicts in the Python projects and developers. With the aid of such results, developers can diagnose their issues, and also our tool is now online. Developers can perform the self-diagnosis service. Yes.
Okay, I also have one question. It seems that you consider the version constraint mechanism in a Python library ecosystem could negatively affect the Python project development. So why the ecosystem still use such mechanism to manage dependencies?
Oh, thank you for your question. The dependency constraint can enable the libraries automatic upgrades, or even can automatically repair their bugs by upgrading to the patched version. However, the library self-evolution can be uncontrollable due to the installation rules of the dependency manager, or can even be affected by the local environment, which can cause dependency conflicts, as discussed in our paper. So in a word, I think the version constraint can indeed benefit the Python ecosystem, but still needs another mechanism or technique like Watchman to maintain and manage the interference between the version constraint across the projects. That's why we developed the Watchman. It looks like a superhero to do this type of work to continuously monitor the dependency conflicts for every Python project in the ecosystem.
Okay, thank you. Thank you for your talk. The next is our last presentation in this session. The presenter is Shurui Zhou. She was a PhD candidate with CMU when she was conducting this work, and now she has become an assistant professor with the University of Toronto in Canada. The paper title is How Has Forking Changed in the Last 20 Years? A study of hard forks on GitHub. So, Shuri, are you ready?
Yeah, can you hear me?
Yeah, I can hear you. We are seeing, yeah, screen. So, okay, perfect. Please go ahead.
All right, thank you very much. Hi, everyone, I'm Shurei. In this talk, I will provide an overview of our study of hard forks on GitHub. This is a joint work with Bogdan and Christian. So a shameless plug first. I just graduated from CMU and will be joining University of Toronto as an assistant professor this fall. I'm actively looking for students at different levels to join my research group. If you're interested, please let me know. Also, CMU ISR, where I just graduated from, is also looking for students to join the software engineering PhD program. If you're interested, please contact us. All right, let's get started. So forking means copying the source code from the original project and then starting an independent development. Traditionally, the goal for forking was to supersede or replace the original one and split off the community. There are various reasons why developers fork. First, a need that cannot be fulfilled by the original project is the most common motivation. Second, some contributors created forks when they feel their feedback is not heard or maintainers are accepting patches too slowly. A recent example is the debating of whether to fork the Docker project or not. Researchers have also found many other motivations, such as discontinuation of an inactive project, or for commercial, legal, or for personal reasons. Traditionally, the forking phenomenon was rare, but there were a few extremely successful forks. Here we present some successful forking events in the timeline. However, in the last around 12 years or so, the fork-based development has been introduced. This is one particular innovation originated by open source and has since spread to commercials that has completely changed how people collaborate to build software systems. These days, there are different social coding platforms supporting this mechanism. The definition of forking is still cloning the upstream and have an independent development, but the motivation has changed to, if you're interested in contributing to the community, please fork the project. This way of developing has been extremely popular with millions of forks. So we have seen two different types of forks. To distinguish these two, we define the old notion of forking, meaning people create forks with the goal of splitting off the community as hard fork, and the GitHub style forking, meaning forking with the intention of contributing back as a social fork. Actually, hard forks have been discussed controversially throughout the history of open source software. And back then, there was a strong norm against forking. As I've talked about before, after the fork-based development was introduced, it has completely changed how people collaborate to build software. Here I'm showing you the timeline of some popular open source platforms based on Google Trend. GitHub is by far the dominant platform and has been key in establishing the social forking phenomenon. Although social forking is super popular right now, we still observed many hard forks exist in the social coding sites. One of the examples that we have seen is this 3D printer firmware community. Nowadays, there are thousands of 3D printers, and actually these are all hard forks of a few original ones. And we've seen people are confused by so many similar projects and struggling about which one should I use as a starting point. So this is essentially the same concern that people had for the traditional forks. Therefore, we are curious about how have perceptions and practices around hard forks changed. As the motivation for forking I've talked about before have been primarily studied on SourceForge before the event of fork-based development. In contrast to a strong norm against forking back then, we conjecture that the promotion of social forks on sites like GitHub may have encouraged forking and lowered the bar also for hard forks. And we argue that it is time to update and deepen our understanding around hard forks in the social coding environment. To achieve our goal, we designed mixed method exploratory research strategy by combining repository mining with interviews. We designed heuristics to identify hard forks, and eventually we collected 15,000 hard forks in total. And then we would like to identify different evolution patterns for hard forks. We first created commit history graphs, which is a customized visualization of commit activities of the fork and the upstream. With these plots, we can quickly inspect development activities before and after the forking point and the interaction between fork and the upstream. And then we use card sorting method to identify common patterns. After several iterations, we arrived at a stable list for 15 patterns. Afterward, we automate the process to analyze all hard forks. Results shows that most hard forks are created as forks of an active project. And there are a substantial number of cases where hard forks are created to revive a dead project. Both the upstream repository and the hard fork remain active for extended periods of time are not very common. So the takeaway message here is that hard fork is still a rare phenomenon nowadays. To explore the motivation and perceptions of hard forks, we conducted 18 interviews for both forks and upstream owners in total. Regarding the motivation of hard forks, the interviewees gave reasons that align well with prior findings. One of the interesting observations is that many hard forks were initially created with the intention of contributing to the upstream, which is actually a social fork. But when they faced obstacles, they decided to continue on their own. For example, one fork owners with over 400 second-level forks mentioned that they started by submitting pull requests to the upstream, but with no responses for 2 months. Then more and more people started to fork their fork. Overall, a theme emerged throughout our interviews is that hard forks are not likely to be avoided, and because of a project's tension between being specific and being general. In this context, a family of related projects that serve slightly different needs or target populations but still coordinate may be a way to balance the trade-off. as our research question is to understand how have perceptions and practices around hard forks changed. The interview result shows that the perception of forking has significantly changed to positive, but we've also heard concerns about community fragmentation. Therefore, we argue that it is necessary to explicitly understand hard forks as part of a larger community. Specifically, we could build a software bot as an early warning system that alerts upstream maintainers of emerging hard forks, which maintainers could use to encourage collaboration over competition and fragmentation. Also, the bot could detect intention and essence of the novel contribution behind the fork. Moreover, designing a dashboard to show how many multiple projects and important hard forks interrelate, as I have shown here, could help developers to maintain an overview of the larger community and encourage potential collaboration opportunities. To summarize, in this study, we automatically detected hard forks and their evolution pattern, and we interviewed open source developers to study the perception and practices in a modern social coding environment. We found that perceptions and practices had indeed changed significantly to positive, but we have also seen concerns of community fragmentation. Last, we also outlined challenges and suggested directions for future research and tooling ideas to facilitate efficient collaboration to build better software ecosystems. Thank you very much.
Okay, thank you, Shuri. We haven't found the question from the audience right now, so please, audience, post your questions. Let me ask a first question. Okay.
Yes, please.
So it seems that this work focuses on hard forks themselves only. So how about, or have you planned to, or have you already considered the contributors who made such hard forks? For example, some contributors created hard forks, and then later they focus on only these hard forks, but some contributors may focus or contribute to both the hard forks and the upstream repositories at the same time. So for example, does this factor will affect the findings in your study?
Yeah, so actually we studied the pairs of hard forks and upstreams, and I think this is a good point that we could understand how multiple forks and upstream interrelate with each other. And based on our current study, I think our preliminary results show that not many forks, they keep synchronizing with the upstream and also kind of implement their own. So if they keep synchronizing with the upstream, we don't consider this as a hard fork. So we have a list of heuristics saying that the hard fork is kind of going out to a different direction and stop interacting with the upstream. And with this, we consider this as a hard fork. But I think your point is because our future research direction is try to understand how hard fork could fit into this larger community and how we could balance the specificity and the generality together.
Okay, yes. Okay, we don't have question for audience. Maybe your presentation is well and they can understand every detail, but still, audience, you're welcome to raise more questions later through the chat window with the authors. Okay, then thank you, Shuri, for your talk.
Thank you.
So here is the end of these 4 presentations in this session. Let's thank the presenters, audience, and the virtualization team. Okay, so this is the end of this session. Thank you all.